Cool. Uh, so till now we have covered how deployment happens. After deployment, what data monitoring we do, what model monitoring we do, and now that we have determined that yes, there is some drift, there is some gap between data and our model. How do we refresh our models? That's the next part that we're going to cover, which is called continuous training. So first thing, which Surendra also covered yesterday, is online learning, which is an extreme case of continuous training where whenever one data point comes, you train it on the go, right? Like one data comes, you don't wait for convergence, you just train it, you update the weights, and then you carry on with the next data point. So this, of course, you don't do this for everything, you do this for specific use cases. And as an example, I will use one case study from Swiggy where we have the routing mechanism. Now you as a customer, you make the payment through card, cash on delivery, whatever, you have some mode. But if you choose card or UPI, there is always a payment gateway behind the scenes. You will not see who is doing that, but some like behind the scenes, it is going through some payment gateway, and there are 3-4 payment gateways. Of course, Swiggy pays to them like just by giving them some amount of money by doing all the routing through them. So what we try to do is we try to keep the customer experience good so that there are no success rates, and all the whatever is the best payment gateway for the customer, we are using that. So for that, we use a multi-armed bandit based model, which basically does the routing part, and it brings in that explore exploit. Yesterday Surendra also mentioned epsilon greedy based method. So we don't use that, but we use a Thompson sampling based method, which basically takes in what was the distribution on each payment gateway during the last 15 minutes, and then based on that it makes the decision which payment gateway to choose. So this happens online, right? Every 15 minutes you get data. There's a near real-time feature running on which computes the distribution for the different payment gateways every 15 minutes, and the model works. So there we it's not exactly online learning, but it is very close to online learning. So that happens constantly. That's the one example. Now getting out of this, now that we have covered online learning, which is not usually the case for every model, I'll come to how we are using feature and data, data and model monitoring alerts to keep our models fresh, which keep away the drift and whatever degradation happens, keep that. Of course, there's a now difference between on demand and always on. Like first model that you'll always deploy would be on demand, right? You'll create the pipeline, you will deploy that model, but it will always be on demand because there is a new use case that you're solving. But once you have deployed it, once you know that it's going to be used everywhere, that's when you start doing that always on part of pipeline, where you would want to keep it fresh. But this is only applicable when your data is non-stationary. But then all the problems that you're solving, like at least in industry, are non-stationary kind of problems because your data changes with time, seasonality comes, people's preferences change, things keep happening, right? So you will do that. So as a case study, recommendation engines, like we discussed in the first part, preferences change. Users decide to order something else after some time. Users have different distribution, different trends come in, and then different seasons come. Based on that, a lot of preferences change, a lot of order patterns change. So we need to keep our models fresh. So recommendation systems are specific examples where we would want to keep the models fresh, right? Because data keeps on changing. Now, how do we keep them fresh? So now that we have detected from model monitoring and data monitoring frameworks that something needs to be refreshed, we start our automated training pipeline, which is of course based on use case, as dependent on some constant time interval. For example, recommendation could be 15 days or 1 month, or in the bandit case routing model, it was 15 minutes. So it can be anything based on what you're doing. In the whole thing, you maintain the state of the pipeline. Basically, like I wrote, right? Here, so you go from raw data to feature store to model. In between, there are different model weights and everything. So there's this lineage always being maintained. That is called the state. Now, let's say you trained a model. Let's take an example of neural model. You trained it today. Now, tomorrow you're refreshing it. Instead of starting from scratch and retraining it, you would want to use the weight from the previous day so that you can warm start it, right? So that's the state part that I'm talking about. And when you're refreshing it, this whole pipeline needs to take that into account. It should also take into account that the tomorrow's refresh that you created, let's say it failed, let's say it was not the right model, or it was not trained properly, then whatever weights that model updated, those are not used for the next warm start. So it handles all of that. Then you do offline experimentations where you do feature engineering, automated, auto ML, and you do everything. You get all the data, metadata in your pipeline, and then either automated validation checks or manual validation checks, you decide whether to push it to production or not. Of course, you don't have to do this whole thing manually. Like, that's why we are creating this continuous training loop, so that everything is automated and you only need to check whether this model needs to be deployed, refresh model or not. And just like I discussed, these are the things that you keep in pipeline state, which is whatever artifacts were there, whatever metadata was there, you warm start, of course. You maintain the whole data lineage between raw till the model end, and of course business metrics as well, and how it performed. And you add automated feature engineering as well, because with time you may need to add more features, previous features may not work. And then these are various tools like which are used in industry. MLflow is like almost integrated with most of the platforms. ML metadata, and there's a very healthy ecosystem around TensorFlow, which Google has provided, because Google is, like, of course, very strong at doing all of these things. And so, on the right is the set of resources that you can follow to actually see how this is all maintained. Is there any question around continuous training, online learning, or sorry, online training, or the whole pipeline? Anything? Cool. Now, business layer. So we have deployed model, right? We did all the process which Surinder talked about yesterday. We formulate the problem, we train the model, we do offline experiments, we finalize the model, we do A/B testing, and then like we do all the deployment. And then we have also added the monitoring layer. But in most of the situations in industry, model output is not usually the final output that is used. There is almost always a business layer on top of it, which caters to different objectives. It could be basically, so like, why is that? Because your model solves a very specific problem. For example, you're predicting ad CTR, right? You are predicting click-through rate, nothing else. But business objectives are different. Like, it might not directly relate to business objectives. So there has to be a layer which basically deals with business objectives as well. So I have 3 different examples. Like, just for example, ad CTR. I have trained model to predict CTR. Yet my model is working well. It is able to put on like show the restaurants which are good at getting the clicks from customers. But even though it's getting clicks, it's not like, these are very small order value restaurants. Like, the orders that people make are very small in value, but business objective is, of course, to earn revenue through orders. So we would want average order value of that restaurant to be higher. So there would be a business layer function, or just another model on top of it, which will basically take in ad CTR model scores and boost it by average order value sort of metric, something that corresponds to average order value, and try to bring in those restaurants within ad slots which are giving me higher order value, right? Because that solves ads problem to have higher CTR, and that also solves average, like my normal order value. So I've improved that as well. And why can't I directly use ad CTR, directly use average or sort by average order value? Because then I remove the personalization between like ads and users affinity. So I can directly solve for just one of the objectives. So I have to get into multiple objectives. Another example is relevance. Say in recommendations, I have recommended that these are the restaurants that should be shown to the user. But again, not all relevant restaurants are something that are business backwards or customer backwards. For example, I've shown you relevant, but it's 20 kilometers away. Even though it's most relevant, most of the users will not order from that restaurant, right? Because it will take a lot of time to reach you. So we would want a sort of layer of last mile distance, the delivery distance, which would keep relevant restaurant, yet the ones which are closer to the restaurant on the top, rather than the most relevant but far away restaurant. Similarly, batching orders versus user perceptions. So when a customer makes an order, a delivery agent is assigned to the order, right? A delivery agent will go to the restaurant, pick up the order, and come to the restaurant or come to the customer. Now we do an optimization so that we save on fuel and delivery time and everything, wherein if on the path of delivery agent there are multiple orders, more than 1, 2, 3, anything, we batch them together so that that delivery agent will pick up those 2, 3 orders and will deliver it to all the people in order, right? Now this has a problem of user perception. Not every user would want that. Like, of course they can see that this is happening, right? And it's taking more time than it should take. Like, there might be cases where user lives nearby and it's taking 30 minutes for the order to be delivered. So that perception, there has to be a perception layer, like that function which encodes this perception into some value, which using which we can decide whether to batch this order or not. So that layer again comes on top. So all the, like, not all the ML model or technical metrics correspond to these business metrics. So there needs to be this business layer on top. Now, how do we solve this? First is, of course, you can have specific business rules, which is very heuristic based. Product manager will do that and all of that. What are automated ways of doing it? So I'll use 2 case studies. One is from Swiggy and another is from Pinterest. At Swiggy, we have a boosting layer, which is basically scalarization of multiple objectives. So it's just alpha times objective 1 plus beta times objective 2. And we arrive at, like, from offline experimentation, what the values of alpha and beta would be. Or it could be alpha times objective 1 plus 1 minus alpha times objective 2. So we just need to arrive at alpha. And then we try to come at some way where even if slight degradation in objective 1 is happening, but more lift is coming from objective 2. So that is what Pareto optimality is, because not everything is directly correlated. If some, like, there are various metrics where if something improves, then something else would go down. So this becomes a multi-objective optimization problem, and we solve it, like, through this layer which we have constructed. Similarly, at Pinterest level, they have a different kind of way of solving this. For example, for them in home feed, they want to maintain distributions for different content. For example, they want to keep that maintain that all the home feed pins, all the home feed posts should contain around 5% of videos. It can be more, but it should not go down lower than 5%. So they have created this solution where they maintain this distribution throughout the session, and it works in real time. So whenever it sees that something is, like, video contribution is going down like below 5%, they quickly start boosting video content higher to bring that distribution back to 5%. And for them, it is more like, so it is still a ranking problem because they are ranking all the feeds, but now they have turned this ranking problem into an optimization problem, because now they still have to rank given some constraints, given video content is greater than equal to 5% or something like that. So using that, they maintain that distribution, and they have this sort of business layer in between. Of course, there are a lot of flaws, and like the last article in the side is what they discuss there, like flaws and what this solves, the whole mathematical formulation and everything. And by the way, this could also be a basically a business problem. Let's say someone came to you that we want to maintain this objective, right? Like we know how to rank, but we still want to maintain uh, various distribution of whatever objectives we want, whatever content we want. And then you'll follow what Surinder talked about yesterday, right? You'll see if data is available, you'll see if it's feasible, you'll see how to formulate it. Like it still needs to be a ranking problem because you need to rank different pins, but how do you turn different business objectives into this? So for us, it became a boosting layer formulation. For Pinterest, it became a controllable distributions formulation. Yeah, this was business layer. Anyone has any doubts, any questions in business layer, anything? Cool. So now horizontal components. By horizontal components, I mean this does not cater to any specific part of the whole data science process, but it is in general related to the complete process, and it applies at a lot of touch points. General things are of course code quality checks, code reviews, code reuse, and like you might, I don't know how many of you are exposed to code quality things, but these things are actually important, and this may not seem important, and data scientists don't really focus on those things, but you should, otherwise you'll see a lot of issues at work. And of course, this last point I want to emphasize, like inefficiencies propagate very easily because you copy code from one notebook or one file to another and just keeps on propagating. And for that, you need to have these code quality, code reuse, and all of this modularization checks in place. As a next step to this, like if you are able to maintain this code quality and code modularization at your, like in your teams, in your projects, in your code, then you can just go one step ahead and create an abstraction, a generic function, which can be added to a module. Similar to pandas, right? In pandas, those guys saw that there was a need for such a model or such a library where you can work on tabular data and do all the data munching, and they created a library out of it. Now they made it generic enough that anybody else could use it, and that's how a module is created. That's how it builds, right? At work, similarly, there'll be a lot of work related things which can be sort of modularized and added to a library, and there will be a lot of that will avoid a lot of boilerplate code. So what happens is many of the inefficiencies come from those boilerplate codes which you are trying to write. So there are several case studies, like at Swiggy, there's DSLib, which we have started to have these abstractions. At Facebook, there are various internal SDKs which does all the things that I've talked in this PPT. Like it will give you feature drifts, it will give you model drifts, it will give you all the hypothesis testing right at the start. It will form a model training loop which will give you all the metrics, precision, recall, coverage, all the curves, all the calibration things, like right at the start. Even if you don't know, you'll at least learn that yes, these are the things exist, and that's how you should train your model. And that comes when they are readily available. Like not everybody is aware of all of these things. Then there are several other tech companies like Spotify, Netflix, Uber, Gojek. Like these are all like right. There's this article which like where I've summarized all of this, and you'll see that ultimately all the tech companies converge to this sort of library structure where they have these abstractions to make the lives of data scientists easier and efficient. This is sample like example because this is from Swiggy, so I know what is there in DSLib. These are various abstractions like to calculate these things. When I joined my team, I was saying there were multiple versions of NDCG itself. Like there were 3-4 versions, and this made things difficult to compare because one guy is calculating NDCG in one way and I am calculating NDCG the other way, and there is no way we can compare both the models. So it makes things very hard. And once you modularize it and makes it like this, everybody starts using one implementation. And of course, this can be peer reviewed, and like all the code checks can be there to make it as efficient as possible. And you can add ML engineers, they can make everything as efficient as you can. So that's the thing, and that's the end of it. If there are any questions, feel free to ask anything. Okay, sure. Yeah. Depends on the companies. For example, the examples that I gave for these Spotify, Netflix, all of them have made their libraries public. So they have made it modularized enough, generic enough that anyone else can use it. And they are very extensive libraries. So yes, they can be. Sorry. Hmm. You can, and there are checks, but it's outside the scope of this whole thing. Well, that doesn't come to us. There are few checks, but those are, for example, we can't use um, discounting data in our recommendation models, right? Because that is sort of giving the advantage to the player who is able to give discounts, not to the player who are not, right? So these kind of checks are there, and we don't really use personally identifiable information in our models. Like we don't, like, we have been asked, plus we don't even try that. And now they've all, like, this happens at data layer end, like they have masked all of this information. It's not even available to us. It's only available when you actually require it. So you need to ask for it, and that you will be given an access for a day or something like that. It's not permanent access. Everything is masked unless you have a special use case and you're using that data. Federated learning.
I think on the Netflix price, right, in that Netflix competition, later when Netflix had made the data available, the data was user ID and the movie IDs data, right? And the ratings that the user had given. Apparently, there was some work later where researchers could um, reverse engineer some information about the users. So there are multiple ways, and that's why I said this field of privacy preserving machine learning has a people are working on.
And there's an adversarial track as well, because you can, so what he's talking is adversarial ML, right? Like, because you figure out from data and you are adding that inside the model, using that information against the model. There are those methods as well, but again, that comes when models are like that, like for example image models, where you can given some examples, you can figure out where the model is working well, where the model is not working well. But we don't do that, and it works for large models. I don't know if there is anything for GPT or normal tree-based model. I'm not sure.
So I just read in a newspaper article that nowadays there is some the chatbot type of thing which is doing the reverse coding for the data. Like therefore, I asked this question. Like if the models, if we can do reverse engineering, the models can be leading to
Yep.
the core of
I
the
have
data.
not seen this for normal tree-based models, but I've seen this happening for neural-based models, like where you can reverse engineering what kind of data it was trained on. Not exactly, but close by. It's an active area of research. It happens, but in industry, I'm not sure how much it is applied, how much it is used. Are there any questions? This is the end. Cool.
Hello.
But it's more, I mean, it's related to data science, but not as much as some of the things that I've learned today. So it's more related to like, you can choose not to answer it. It's a little bit loaded, it's a little bit edgy, but recently I came across this article saying that food delivery apps like Swiggy and Zomato charge a little bit extra onto the food costs as well, because or in app, for example, if something's worth X amount on the menu in the restaurant, so we would charge 1.1 or 1.25 or 1.5x. I haven't experienced that yet on Swiggy, or even when I'm in the UK, I haven't. But do you think, because Swiggy has so many offers for free delivery and 50% off or 60% off up to a certain amount, do you think that that amount is justified, even if Swiggy does charge that? Again, you can choose not to answer it.
Let's choose not to answer this. Maybe we can discuss it offline. That will be my opinion. It will not be Swiggy's opinion, right? So I don't want to discuss that.